Good evening to all. Thanks for joining. This is Kousik Devan, one of the TAs for the course Foundation Engineering conducted by NPTEL. Our course instructor is Professor Kousik Deb from IIT Kharagpur. My fellow TA is Mr. Shivshankar Nandi from IIT Kanpur. Okay. So let's begin today's session. This is regarding week 10. So we'll be solving a couple of problems in week 10. Just for as a recap, um, week 10 began by our instructor solving a few problems on lateral earth pressure for layered cohesive soils, like with different conditions, with different order of layers, like cohesive and cohesionless soils, and stronger and weaker soils in top and bottom in all the possible manner. So he solved a lot of problems, and I hope it's clear. And then he moved on to Coulomb's earth pressure theory. So till now we were dealing with Rankine's earth pressure theory. All the extensions and all the special case scenarios were extended, which was the basis of Rankine's pressure theory. Here in this week we moved on to Coulomb's earth pressure theory, wherein there are only small differences. In Rankine's pressure theory, we began in the initial assumptions. We assumed our backfill as horizontal, and also the back of the wall was supposed to be horizontal, and there was no friction between the wall and the soil. So Coulomb, what he did is he incorporated all these things, and he did normal static analysis, taking the wedge of the failure wedge as a rigid body. So if we have if this was Rankine's backfill, now we in Coulomb's backfill we can have something like this. This means that the backfill can be inclined as well as the back of the wall can be inclined. Sorry. And so this scenario can be directly used. So in Coulomb's theory, we are assuming that the failure wedge, that is this triangle of the soil, will move fail as a rigid body, and all the frictions involved in this surface as well as this surface is accounted. So it can be extended as a graphical method also. There are different methods like Kalman's method and Rippon's method. And so that's the thing. So here we have our in the wall we have the friction, walls friction. So if we are having a PA, that it will make an angle with the normal to the wall as delta, where delta is the angle of interfacial friction between our wall material, whether it is masonry or concrete. So wall and soil. So this is just like any other frictional angle that we say. This is in between two materials. So this is generally expressed in terms of a ratio with the phi value. So with different materials like concrete and wood, or masonry or steel, it will have different delta value. We have dealt with this in pile foundation as well, so it's not new to us. So Coulomb incorporated that also. So we have all the three more things taken into account, and after discussing the Coulomb's theory, we proceeded with different types of retaining walls. When I say retaining walls, these three types are based on the the resistance provided by the retaining wall, whether it is from the self weight gravity, or whether it is from the beam action, or the beam frictional resistance of the stem of the retaining wall. So that on the base of that we can divide it to these three, and whether it is counterfort retaining wall or buttress retaining wall. So this is on the basis when we have to retain a higher backfill, we will have to come up with either counterfort wall or buttressed wall. We will see a few picture in the next slide, and after that we we solved a lot of design problems, two three design problems on gravity retaining wall and cantilever retaining wall. So both the methods, like he started with Coulomb's theory, earth pressure theory method in the first question, and the second question was partially completed, which was done by Rankine's theory. So then since I was talking about different types of I just thought of just touching upon it. So this is these three are based on these actions. First, top three are based on its action against used for resisting our retaining wall. Sorry, our backfill. So to resist our backfill, this particular thing is solely dependent on the self weight of the soil. Self weight of the material. So our cross section has to be a bigger one. So it's quite clear. So before the use of steel as a reinforcement, the people used to go for this particular wall. Masonry was used, or earth, even earthen dam is one of the examples, and even concrete can be used for gravity retaining walls. So the idea is the weight of the material is in turn resisting our lateral pressure exerted by the backfill. So hence its a cross section is very big. After introduction of steel, we reduced it a little bit. We were not confident much in the beginning. So if you want a adaptive design, we can go for steel, and it will drastically reduce the cross section area of the material requirement of the, whether it is masonry or steel or concrete. It can be reduced by providing our steel as a reinforcement, because since earth pressure is acting like this, our section cross section has a tendency to be under tension in this region. So we can provide wherever tension is there. So in this phase is expected to face some tension, so we are providing reinforcement. So, and next thing is as a cantilever. So this is just like a cantilever retaining wall, means it's just like a cantilever beam. So this retaining wall is reinforced with steel. So it's as equivalent as this one. If I'm supposing a beam and its load is like this cantilever beam, and it's fixed at one end and free at the other end. So this is equivalent as this. So that's why it is called a cantilever retaining wall. Now the other two, counterfort retaining wall and buttress retaining wall, there is a very subtle difference. Counterfort retaining wall, these both are generally when the height of the backfill is quite high, if we are to achieve. So one is like our extra member, that is counterfort, is inside the backfill, that is in the counterfort retaining wall, and buttress means our extra member which resists our deformation of the stem is away from the backfill. So if you are able to see this particular member, it's you can conclude that this buttressed retaining wall. Okay, so having said that, let's move on to the first question. So what I have chosen here is Coulomb's theory. Using Coulomb's theory, how can we solve how can we find the lateral pressure? So this is a very simple question wherein we are asked, we know the height of the wall, masonry retaining wall, granular soil. So Coulomb's theory is initially proposed only for granular soil backfill, and it was later extended, which becomes more complex. It was later extended for cohesive soils also. But in this stage, we are only discussing about granular backfill. So in granular backfill, angular friction, so phi value is given, and the back face of the wall is inclined to the vertical positive batter angle. So back face, the inclination of the backfill, the vertical is also given, and backfill is sloping upward. So our backfill is inclined. So that is also given. And assuming the angle of internal friction, angle of wall friction. So angle of wall friction is what I told as delta earlier. It is nothing but the interfacial friction between the wall and the soil. So whichever two material we have, it will have a interfacial friction, and it will be less than 5 generally. And in this case of wall, we generally take it by 2 by 3 or 3 by 4 of 5. So in this case they have already given, so we need not worry about what value to assume. So basically this angle is angle of internal friction between wall and the solid. So we are supposed to calculate total active earth pressure and on the wall per meter length if the density of the backfill is 18.9. So we have the details uh, given. So we have this equation. So here in this equation what we have is alpha is nothing but we have the angle, it's the angle of inclination of our back side of the wall with the horizontal. So we have that. So if we have uh, this as our wall and this as our backfill, we have this as alpha. So alpha is done. Phi we already know for the soil, and delta we know that it's the, if this is the perpendicular, our load will act at an angle of delta with the surface. So it's true for any surface, like in the sense if we have the angle of friction between any surface, the load will act in that angle. So that is there, and we have inclination I. So I is also done. Alpha is there, phi is there. So we know all the values, we just have to substitute. But here um, one thing is like I is given in 10 to the power 10 is to 1. So that means that this is 10 and this is 1. So I have to find it here before itself. So I can write it as tan inverse of so this is, since this is 10 is to 1, so vertical by horizontal, so 1 by 10. Tan inverse of 1 by 10 will be 5.71 degrees. So our I is 5.71 degree. So that is the only thing that they have given indirectly. So I can substitute the values now directly. So so yeah, this is the figure I was talking about. So here I have alpha. So this is alpha, and this is our I, which is 5.71 degrees. So this is 10 is to 1. Obviously it's not for scale, I'm just trying to illustrate it. So this is also I. So because this is, I'm trying to take it as 90 degree. Now my load, end load, like the active earth pressure thrust, will act at an angle of delta. uh, okay. Now what else? Yeah, what is the angle we are given? We are given back face of the wall is inclined with an inclined to the vertical at an angle of 12 degrees. So our this angle with the vertical is 12 degrees. So our alpha, so this is also 12 degree. So alpha is equal to 90 minus 12 degree, that is 78 degree. So we have alpha is equal to 78 degree. uh, Delta we are already given as 16 degree, and our phi value is 32 degree, and our gamma is 18.9 kilometer per meter cube. So it's also said that this is at a height of h by k. Okay, so total height is 6 meter. Okay, so if I'm substituting, if I'm trying to find ka value, I have to write, I'm writing the same formula by substituting the values. So ka in the numerator I have sine of alpha, a sine square of alpha plus phi. So our alpha is 78 plus phi is 32. In the denominator we have sine square of alpha, that is 78, into sine of alpha minus delta, that is 78 minus 16, and we have a huge bracket, 1 plus root of um, 1 plus root of sine of phi plus delta. So phi plus delta is 32 plus 16 into sine phi minus I, that is 32 minus 5.71, divided by sine of alpha minus delta. Alpha is 78 minus delta is 16, sine alpha plus I, that is 78 plus 5.71. So this whole bracket has to be squared. So this is our Ka equation. If we solve it, we will get it as 0.402. So then rest everything is same as we had done before. So our total lateral earth pressure sorry, active is PA is equal to half into Ka gamma H square. Okay, so this is half into 0.402 into gamma is 18.9 into H square is C square. So we have 136.83. So that's how we find the lateral pressure. So here we have this value 136.83 kilometer. We have at an angle of 16 degrees. So uh, h by 3, so this will be obviously 2 meter, so that we know the location of the this thing, the total load. Okay, so this is just substituting the formula. We will move on with the problem where we have to design the retaining wall. In the sense, design in the sense, either it could be finding the dimension, or it can be checking the stability. So here we'll check the stability. So we'll be given a cross section and all. Uh, we are supposed to find the lateral pressure and factor of safety in different conditions and all. That is what checking the factor of safety is nothing but checking the stability. So we have different ways of finding this, checking the stability. One thing is, primary thing is checking whether it is failing by bearing capacity. Another thing is checking whether it is overturning, like whether the our dam, our retaining structure is subjected to overturn. That is a resisting moment and the overturning moment. So overturning moment, when it's overwhelmed, like it's too much, and it goes beyond our resisting moment, it will overturn, so it will turn. So that is a safety against overturning. And we have sliding. So if the base is weak, and if our horizontal force due to our lateral earth pressure, if it is exceeding our resistance, lateral resistance at the base provided by our soil, if it is exceeding that, it will cause sliding, right? So what is the safety factor safety in sliding? And we also need to design the structure in such a way that it should not have any tension at the base. So in the sense, when we are dealing with a load which is eccentric, so generally all the loads will be eccentric in the case of retaining walls, because it will keep on changing the weight from the backfill will keep on changing, and there will be at least some eccentricity in the real case scenario. So when we have an eccentric load, our stresses at the base won't be uniform. So we should make sure that the least stress is not less than zero, which means that it should be always compressive. It should not be tensile, because our soil is weak in tension. So that is one of the things. So we will check these things and check whether our this particular section is safe or not. So we have a gravity retaining wall made of concrete. So we have the density of concrete. We need the density of concrete because it's gravity retaining wall, so its self weight has to be considered. And check the stability of the retaining wall. Adhesion factor is given as 9. So adhesion factor we require because at the base uh, we have to find the shear strength of the soil with the base. For that we need adhesion with the concrete as the soil. And property of subsoil and backfill. So subsoil and backfill. So there are two different soils we are mentioning here. Backfill means whatever soil is behind the retaining wall. So we will use it for our Ka calculation and our weight calculations and all of the for lateral earth pressure calculations. Subsoil, we need to find we need to check the stability, like the capacity of the soil, bearing capacity, as well as our sliding is to check the stability against sliding. We need backfill soil property. So generally, since it is a matter of a few meters, the property will change. That's why we are mentioning it separately. Okay. So having said that, we have a particular section given here. So this is the section we have. So here the height is I forgot to mention the height. The height is nothing but 5 meter. So this height is 5 meter. So if we have a section like this, how can we check the stability? So let us just write down. So there are two approaches. One approach is what we are going to do now. That is our Coulomb's theory. So that when I say Coulomb's theory, what it means that there will be a load here at the end, PA. So we can resolve it into a vertical and a horizontal load, and we can treat it as a one vertical and a horizontal load, and we can check the self weights of each. So we will do, since it is a gravity retaining wall, we can check the weight of each portion. We can divide the cross section into four parts here, and let it be like one, uh, two, three, and four. So all this we can add, and we'll get our self weight of the gram, and we'll have two more loads. That is our resolution of our lateral earth pressure load. Using Kalman's, we can do that. Another option is using Rankine. So in Rankine's method, what we do is instead of using this Kalman's uh, method, what we can do is we will divide till here, till the heel of the retaining wall. So we can we can assume that this soil also will consider as contributing for resisting moment, and we will check the lateral earth pressure here. So we'll have a horizontal lateral earth pressure. Using Rankine's theory, we can get the k value, and using that we can calculate that, and we will end up getting uh, this 1 2 3 4 5 6 7 7 loads. So the self weight of the soil is also considered, because it will so since we are taking moment at this point, if we are taking moment at this point, all the weights, that is concrete weights and the soil's weight will contribute for resisting moment, and the lateral load will contribute for the overturning moment. So if you can imagine the horizontal load, the the lateral earth pressure load, that will contribute to overturn the retaining wall, and the other loads will cause the restoring moment. Okay, so this is a Rankine's, using Rankine's, but the thing is, like, when we use Rankine's theory, there is a particular law that this particular angle should not exceed a particular value. So this angle this alpha should not cross 45. So what I mean to say is that if we find a value 45, actually sir has already discussed this, but if it is not clear, I wanted to explain. So we have what we'll do is we'll find the value of alpha, and that is 45 plus 5 by 2 minus I by 2 plus sine inverse of sine I by sine phi. And if we find that alpha, and if I draw this line, if it is crossing the stem like this, then we cannot use Rankine's this particular method. But if it is not crossing, if it is in this area, or if it is just touching this particular point, then there is no issue. We can go for the method that we are talking. But here, now in this question, we will use our Coulomb's method. So in Coulomb's method, as I told before, we will directly take the load on the wall. So our load is acting on the wall. So it's like this TA, and our this value will be delta, and this value is nothing but, if this is beta, this is our beta, and what else? Okay, so we can resolve this as two loads. If I'm right using another color, I can resolve this as PAV and PAH. So I can resolve it into two, and this along with other values like our self weight values like W1, W3, W2, and W4. PAV will be also causing restoring moment, and PAH will cause a overturning moment. So we'll find the value of all this. That is the next step. So before that, let us find these soil properties. Let us get clarified with the soil properties. So here we have delta is given in terms of phi. So let us just find that first. So here we have subsoils delta value is 75% of phi value, and that will be uh, 22 into 0.7, that is 16.5, and 2 by 3 of phi is for backfill, that is 24 degree. So we have delta values, c values. So if I am just writing it here, I'll do one thing and write it as black in this, that is subsoil properties, that is c is equal to 20 kPa, and delta is equal to 16.5 kPa, and alpha is equal to zero point 0.9, which is already given in the question. Phi value is equal to 36. Is it 36? Sorry, 22. So 22 degrees, and gamma is equal to 20 kilonewton per meter cube. So we have the properties of the subsoil for the backfill soil. We have phi is equal to 36 degree, gamma is equal to 19.5 kilonewton per meter cube, and delta is equal to 24. So that means this is 24 degree, and what else? I here I is equal to 0, so that is not an issue, and okay, that's it, I guess. So alpha here, if I'm writing beta, so if I want to find beta, uh, okay, beta, if this is beta, uh, this is 0.75, so I can write beta is equal to tan inverse of opposite by height. Opposite is 0.8 by 5.75. This is 5 plus 0.75. This will be almost 8 degrees, right? Okay, so beta we have 8 degrees, so this is also 8 degrees, and this will be our uh, alpha in the other term. So this angle I will write it as uh, this is 8 means this is 90 minus 8, that is 82 degrees. Okay. So we know the angles, we can directly substitute and get the k naught value. So what I'll do is, in Coulomb's theory we have active earth pressure coefficient equation, that is Ka is equal to sine inverse of alpha plus phi by sine square of alpha, and sorry, sine square of alpha, sine of alpha minus delta, 1 plus root sine phi plus delta, sine phi minus I divided by sine alpha minus delta, sine alpha, sorry, sine alpha plus I. So this whole bracket square, if we substitute the values as alpha is equal to 82 degree, don't confuse this alpha with our adhesion. That is, adhesion is for that is a constant which is for our subsoil property. Delta is, if I substitute delta is equal to 24 degree, and phi is equal to 36 degree, and I is equal to 0. So I is equal to 0 here. So let me substitute that. So if I substitute sine square 82 plus 36 divided by sine square 82 sine of 82 minus delta is 24, 1 plus root of sine of 36 minus 24, sorry, 36 plus 24, sine of 36 minus I, so I is 0, so I will not write I, and sine of 82 minus 24 and sine of 82. Okay, this whole square. So this turns out to be 0.296. So I have everything. I can directly calculate PA. Our total PA I can write it as PA is equal to half into Ka gamma H square. So here my H is the whole length, that is from here to here, the base of the footing. So that is 5 plus 0.75 plus zero point 0.5, or 5 plus 1.25, so that is 6.25. So I can write it as uh, half into 0.296 into 19.5 into 6.25 square. This is 112.75 kilonewton per meter. So we know PA, that is 112.75 kilonewton per meter. So it should not be per meter square, it should be per meter. Per meter in the sense per meter length. So we are, since this is a plane strain problem, we are assuming just 1 meter length of the retaining wall. So this is the total load in that 1 meter. So we got the total load. So let us resolve now. So when we resolve now to PAV and PAH, our total angle is delta plus beta, that is 24 plus 8, right? So I can resolve this as uh, PAV, that is a vertical component. I can write it as PA sine of delta plus beta, that is 112.75 into sine of delta is 24 plus 8. This is 95.62 kilonewton per meter. And PAH, the horizontal component. Horizontal component I can write it as PA cos of delta plus beta, that is will be 112.75 cos of 24 plus 8. This is 59.74. Sorry, it's the other way, because cos, okay, so this is 95.62 and this is 59.75, because it's less than 45, so it cos has to be higher. So it looks like this. If I have a PA, if this is PA, I can resolve it as, this is my beta plus delta, that is 24 plus 8 is 32 degree, and this will be my 95.62, that is PAH, and this is my PAV, that is 59.74. So that's how it is. Now we can proceed further. What we'll do is, we will find out all the loads involved. That is, now we know PAV and PAH, but we don't know W1, W2, W3, W4, and we don't know the moments also. So in a tabular format, we will can, so that it's clearer. So I'll write one thing. I'll name one here. So if I'm writing the first one as W1, okay. So I'll use blue color for restoring moments. So I'll write this as W1. So my W1 is, so let me make it clear. So this is my W1. We have a rectangle. So the rectangular dimension. So I'll write volume into density of concrete. That will be the vertical load, right? Self weight. So the volume will be the total 5.75 into zero point 0.4 into 1 into 24. So this is the volume and this is the density. So we have 55.555 kilometer. So why it is 5.75? Because the stem, I am talking about this rectangle, so it is still 5 plus 0.75, so 5.7, and the width is zero point 0.4. Similarly, if I go for the second one, the triangle, sorry, the second one, yeah, so the second one is the base. So this base, if I'm going for the base, the thickness is zero point 0.5, the length, if I add everything, it comes out to be 3.6 meter. So I can write it as W2 is zero point 0.5 into 3.6 into 1, this is the volume, into 24 kilonewton per meter cube is the density of concrete. This turns out to be 43.2 kilometer. Okay, so I need not write kilometer. So third one is W3, that is a triangle. So we have a triangle here, base is zero point 0.8 and height is 5.75. So that triangle is half into zero point 0.8 into 5.75 into 24. This is 55.2 kilometer. We all know that the fourth one, that is this triangle, is also of the same dimension, fourth triangle figure. So I can write the same value, that is a volume will be the same. So this will be also be 55.2 kilometer, that is half into zero point 0.8 into 5.75 into 24. So the fifth figure, so fifth load is also restoring, that is our PAV. So our PAV is causing a restoring moment. So if you look at this point O, from the point O, if you look at PAV, it is not it is causing a restoring moment. So I'll write PAV, that value I already know, that is total 59.74. But my sixth load, that is my horizontal force due to the lateral earth pressure, that is causing the overturning moment. So I'll write that in this column, that is sixth one is PAH, that will be for 95.62 kilometer. So the rest everything is not applicable. So lever arm is nothing but what is our distance from, of these forces from the point of reference. So here I am keeping the base point at the toe as the point of reference, that is O. So for each point, so for example for one it is at the middle, so this distance of this O from this middle is zero point 0.8 plus 0.8 plus 0.4 by 2. So I can write it as 0.8 plus 0.8 plus 0.4 by 2, that is 1.8. So this will be 1.8, oh, sorry, 1.8 meter. And next one, W2 is also in the same line. So my W2 is also this 3.6 by 2, that is 1.8. My W3, that is this triangle. This triangle, if I want, I have to get zero point 0.8 plus 2 by 3 of zero point 0.8. That is from the from this distance, that is 2 by 3. So 8.8 plus 0 0.8 plus 2 by 3 of zero point 0.8. This is 1.33 meter. And the W4, that is this particular distance I need, that is 0.8 plus 0.8 plus 0.4 plus 1 by 3 of zero point 0.8. So here it's near to the vertical side, so this distance is 1 by 3 of base. So I can write it as 0.8 plus 0.8 point, sorry, what is it, okay, so 0.8 plus 0.8 plus 0.4 plus 0.8 by 3. So this value is 2.267. And we have PAV. PAV is quite tricky because it's acting on the sloping side, so we need to find the this value, that is if I if this is that portion of the inclined wall, and our PV is acting here, so I need to find this distance to get the horizontal. So this distance is nothing but uh, here I know. Okay, I'll try to locate this first. So this height is actually uh, okay, so we have 82 degrees. We know the angle, this angle is 82 degrees, and we also know that this distance, we can find this distance. What is that distance? That distance is this one. So I told you that the height, the point of application of the load is at a distance of h by 3. So our h by 3 is actually here, that is 6.25 by 3, and that will be 6.25 divided by 3, it is 2.08. 2.08. So in this 2.08 I have to subtract zero point 0.5, that will be so this distance will be 2.08 minus zero point 0.5, that is 1.53. So I can write this as this x is equal to uh, opposite. So this 2.08 minus zero point 0.5 divided by tan of 82. I can write opposite by hypotenuse. So opposite by adjacent. So this turns out to be tan of 82. So this is 0.22. So my this distance is 0.22. So from our point of reference, that is O, if this is point of 22, mine I can write it as uh, 3.6 minus zero point 0.8 minus 0.22. So that is my distance will be 3.6 minus zero point 0.8 minus 0.22. This lever arm is uh, 2.578. Okay, so we have lever arms for resisting moments. Now what is the lever arm for our horizontal force? That is the total distance, that is 2.08. So my this distance will be 2.08, that is nothing but my h by 3. So at the from the base my distance is 2.08 meters. So we have everything. If we just multiply our load versus lever arm, we'll get our moment. So the resisting moment is 50. This, for example, the first weight is 55 into 1.8, so that is 99. If you just multiply, you'll get it. uh, Second one is 43.2 into 1.8, that will be 77.76. Third one is for 55.2 into 1.33, that will be 73.42. Third one is 55.2 versus into 2.27, that is 125.14. And the last fifth one is 59.74 into 2.57, that is 154 point, okay, 154. So what about our so these things will be vacant, and for my overturning moment it will be 95.62 into 2.08, that will be 198.89. So this is a procedure to tabulate our moments, restoring moments and overturning moments. It's very important how to identify these moments, which is restoring and which is If you just take one point as a reference, and if you just say the direction of the forces, whether it is causing a clockwise moment or an anti-clockwise moment, you can figure out which is resisting moment and or overturning moment. So here in this case we have only one overturning moment. So what we are supposed to do is we are supposed to find the total. So for example, here we have total for vertical load as, if you add all the things, we get 268.34 kilonewton. And if you add everything in the horizontal direction, we have only one, so we can write it as 95.62 kilonewton. And if we add all the restoring moments, that is our sorry, I'll rather write this in blue color so that there is no confusion. uh, in the force, it doesn't play much role, but in this moment I should stick to the color code. So in the restoring moment, if I add all the restoring moments, I'll get total restoring moments. I'm writing it as MR as 531.24. Sorry, MR is equal to 531.24 kilometer. The decimal rounding decimals can be a little different. So if you are working out on your own, please see to it. Then another overturning moment, I write it as MO, that is 198.89 kilonewton meter. Okay, so we have all the ingredients. Now we can just go for the stability analysis. Now to check overturning. So overturning is as simple as I told you. So we have a point here. One moment is trying to overturn our structure, and the restoring moment is trying to restore. So MR. So if I just see its ratio, I'll get the factor of safety against overturning. So first factor of safety against overturning, that I can write it as MR by NO. So this is 531.24 divided by 198.89. So this value is 2.67. So isn't it 2.67? 531. Yeah, 2.67. So this particular value here, what we got, it should be between 1.5 to 2 at least, generally, this factorosity. So here it is fine, so hence it is stable against overturning. That is the first check. The second one is factor of safety against, okay, not factor of safety, we have to check whether there is no tension. So I as I mentioned earlier, I have to check oh, sorry. So check for no tension. So the idea is we will have two different stress values, F1 and F2, and this F2, the smaller value should never be less than 0. So it should not have be a value which will cause tension. So if it is negative in this case, it will be tension. So that is given as F1 F2 is given as sigma V by B 1 plus or minus 6E by B. So 6E by B, where E is the eccentricity. So here if you see the minimum value, that is our F2, if this is F2, so F2 is sigma V by B 1 minus 6E by B. So if I am equating this to 0, I'll get 1 minus 6E by B as 0, and I'll get E is equal to B by 6. So this is the limit where it changes to 0. Excuse me, I'll write it properly. So this is the condition where it should not cross. So what we'll do is we'll find the eccentricity. To find the eccentricity, what we need is x bar. So x bar is the position of eccentricity from our reference point. So position of eccentricity from our reference point is mr minus mo divided by our sigma b. So this is the horizontal distance from the result of the resultant from our reference point. If you want to find the horizontal distance from the result reference point, we need to this is the formula. So we will get 531.24 minus 198.89 divided by vertical force is 268.34. This is 1.234. So this is our position of our so if this is the base and this is our reference point, our position of our load, that is resultant from the this point, is this is our x bar. So the horizontal distance from the, so our eccentricity what we require is this thing from the center of the base. So eccentricity is equal to b by 2 minus x bar, that is 3.6 by 2 minus 1.23, that will be 0.566. And what is our this must be less than b by 6. So b by 6 is uh, 3.6 by 6, that is 0.6. So it's just less than our so it's okay, so it's safe, there will be no tension. So hence no tension will be developed at the base. So that is a check for no tension. uh, so all the checks till now it's fine. Let's go for the next one. The next one is bearing, checking against bearing capacity. We can do this in two ways. One is by till what we had done for shallow foundation, we since it is eccentric load, we have done already for eccentric load. So shallow foundation eccentric load I can do. So in that case, my B will change to B dash after subtracting the eccentric load. B dash is equal to B minus 2EX. Using this, I can just as usual, if you remember the older one. Another option is I can go for I can find the Q max, that is nothing but our F1 that I was talking about here. F1 that is sigma V by V 1 plus 6E by B, and I can compare it with our QNU. But here I should find the QNU from B. Here I am finding QNU, that is our capacity from B dash. So that I have to remember. So if I'm using the updated base, I have to use the shallow foundation. So either of these methods. So here our Qmax, my factor of safety will be QNU by Qmax. Here my factor of safety will be whatever load I will find the total load and I will divide it by. So let us check. So here I'll do only one method. I'll do the upper one, the shallow foundation one. So I'll use it. I'll imagine it as a shallow foundation. So my equation is QNU is equal to QU minus gamma DF. This is equal to CNC. I hope you remember this thing. We had done this before. CNC, SCDC, IC, the IS code for the Meyerhof, whatever the Meyerhof came up with, NQ, SQ, DQ, IQ plus half gamma B N gamma, S gamma, D gamma, I gamma So this is like, so we need to find the other factors, correction factors. So let us find each of them. So before that, so here I need to emphasize that this we are dealing with bearing capacity. So we have to use our subsoil properties. So the soil which is near to the base. So I have the value. So first of all, let me find this NC, NQ, and gamma. So NC, NQ, and N gamma. I can get it from my IS code or Meyerhof table, whichever it's available. So our particular phi value is 22 degree. That is for the base properties. I have phi value as 22 degree. So for corresponding to 22 degree, so we have for 20 and 25, we are supposed to interpolate these two values for NC and gamma. I already interpolated, so I just show one example. So for finding NC for 22 degree, I have uh, NC for 22 degree. I can find it as 14.83 plus 20.72 minus 14.83 divided by the difference of this 20 and 25 is 5, and my difference is 22 minus 20. So if I use this formula, I can get my value as 17.19. So that's how we interpolate. Interpolation is a very basic thing we can learn from anywhere. So NC will be 17.919. Similarly, we can interpolate these two values and these two values for NQ and N gamma. That is 8.1 and 7.59. That is our bearing capacity factors. Now let us see what is our shape factor. So shape factors, SC, SQ, and S gamma will be equal to 1, because here we are dealing it as a strip footing. So similarly to strip footing, we are hypothesizing this as a strip footing. So shape factor won't have any problem. Another next thing is our uh, depth factor, right? So depth factor is dc dq d gamma. So dc, for depth factor, before we use, we need to find the our updated breadth. So our updated breadth is b minus 2 eccentricity, that is 3.6 minus 2 into 0.566. This is 2.47 meter, and our depth of foundation is nothing but 1.25, because it is 0.75 plus zero point 0.5, so 1.25. So depth of we have. So depth factor, to find depth factor we need a dc. So dc is equal to, so this you will get from our code 1603, df by b tan of 45 plus 5 by 2. So here this b, instead of, we have to use b dash. That is 1 plus zero point 0.2 into df is 1.25 by 2.47, divided into tan of 45 plus 5 by 2, that is 22 by 2. This is 1.15, and our dq and d gamma is equal to similarly 0.1 df by b, similar equation 45 plus 5 by 2. If you substitute this, you will get 1.07. The next one is inclination. So here our load is inclined, right? So our we have vertical loads as well as horizontal loads. Sorry, vertical loads as well as horizontal loads. So I can write our IC is equal to IQ. IC is equal to IQ is equal to 1 minus alpha by 90 whole square. So this is equal to 1 minus our alpha. So what is alpha? This alpha is nothing but our angle of inclination of our load. So our resultant load, this is our alpha. So I have vertical and I have horizontal. So I can write alpha as tan inverse of horizontal by vertical. That is nothing but tan inverse of horizontal load is nothing but 95.62. Vertical load sum is 268.34. If you substitute this, you will get alpha as 19.61. So here my alpha is 19.61 divided by 90 whole square. This turns out to be 0.6117. And our I gamma is 1 minus alpha by 5 whole square. So this will be 1 minus 19.61 by 22 whole square. This will be 0.0118. So it's a very small value. So our third term is going to be reduced over. Now we can just directly substitute. Let us see what happens. So our Q and U is equal to in Meyerhoff's it's QU minus gamma df. So I'll write QU, that is our whole here I was supposed to write minus gamma df, this gamma df. So I can write I'm substituting the whole values. I'm using this equation just to clarify. I'm going to substitute all the values. I know it looks a little clumsy, but I hope you understand. So if I substitute all the values, I'll get, I'm going to write the value. So 17.19, this is CNC into DC IC plus uh, instead of Q 1.25. This is my gamma into DF into NQ. NQ is 8.1 into 1.075 DQ. Sorry, DQ IQ, that is 0.611. The third term is half gamma B. Here I am writing B dash. Sorry. So B dash. N gamma is 7.59. D gamma is 1.075. And our I gamma is 0.018. And minus our gamma df. So df into gamma. So if you add all this, you will get 377.85. If this is our capacity, what is the ultimate load that it can carry? Ultimate load that it can carry is nothing but our Q and U into B dash. That is 377.385 into B dash is 2.47. This is 932.17 kilometer per meter. So what is the load acting right now? That is our sigma V, right? So that is 268.34. So I can write that the factor of safety is equal to Q and U by sigma V. That is 930 932.17 by 268.34. This will be 3.46. This is supposed to be greater than 2.523. So there are different so this is a general adopted factor of safety. So here it's okay, so hence it is stable against our bearing capacity. So it has passed the first 3-step tests now. Check. So our last check is our against sliding. So what we are doing is we can fourth, stability against sliding. So what is happening is we have a surface here and we are trying to push it push it with a horizontal force. So this is our horizontal force. We are trying to push it in one direction and there will be resistance in another direction. So this is the resisting force. So this resisting force I can write it as uh, CA, so the adhesion, so adhesion into uh, B dash, so whatever the length, so the whole length, plus uh, gamma, this normal force sigma V tan delta. So there are two components, just like our C plus sigma V tan delta. Yeah, C plus sigma V tan delta. I can write it in terms, that was in terms of stress. Here I am writing in terms of force. So in order to write in terms of force, I am writing it CA into B. So this is a force, and this is already a force into tan delta. That is a frictional force resisting. So our factor of race safety, I can directly write it as factor of safety against sliding. I can write it as CA, that is adhesion, into B dash plus sigma V tan delta divided by the driving force. This is a resisting force. Denominator we have driving force as sigma H. Again, this CA is nothing but C into alpha. So I have C as 20 and alpha as zero point 0.9. So I can directly write it there. So I write 20 into zero point 0.9 into B dash is 2.47 plus 268.34 into tan. Our delta was 16.5 for the sub-base oil. Uh, delta H is 95.62. This is actually 1.269. Sorry, the other way. 1.296. Factor of safety against sliding is supposed to be, it is supposed to be higher than 1.5. So, but this is less than 1.5. So here it is not satisfied. So unstable, unstable against. So our fourth check, that is against sliding, that is not satisfied. Here we have 1.296 and it was supposed to be greater than 1.5. So uh, there are some people may argue that this B dash should be taken as 3.6, not 2.4, sorry, not 2.47, but this is our corrected 2.47 with respect to by considering eccentricity. If you take 3.6, it might be just higher than 1.5, but my point is if we are taking 2.47, it's less than 1.5, so we have to increase it somehow. So one solution that we can adopt is ground improvement at the base. So before we construct, we can improve the ground so that our delta is increased. So to improve, sorry, ground improvement at base. So what I'm trying to say is we are trying to increase delta by improving the soil at the base. So ground improvement by, okay, sorry, at the base to increase our delta value. Okay, so that is one solution. Another solution, there are many things we can provide. A shear key. Shear key is nothing but if we have a base slab, instead of a base slab like this, we can also give a extra notch like part so that it will resist against sliding. So there are different things we can also uh, readjust our so we can increase the base, increase base, but that will also, but all the things will govern, the cost will, economics will govern which solution we are trying to go for. So these are different solutions. So the fourth check, that is check against level stability, didn't satisfy. So That is the thing here. Now, did I miss out anything? So we have these things. So it's safe against overturn. It is there is no tension developed at the base. It is safe against a bearing failure. It is not safe against sliding. So that is what we have to take care in this particular case. So in the question there might be if we are designing, suppose we are trying to design. So in the next iteration we are supposed to come up do any of these solutions that we are suggesting, which can improve our resistance against sliding. So this is the way to do using our Coulomb's theory. That is, we used this formula, our Coulomb's theory we used, and as I told, we can also do it by Rankine's method. I think if I'm not wrong, this week ended up by Sir solving cantilever retaining wall using Rankine's method. It was not completed, that's why I didn't take up that. So we'll hopefully do it in the next week, or so I hope everything is clear. The in a similar problem is also solved in the week, so I would suggest you to go through that also. So just to wind up, I would just go for small MCQ questions. So this is what we are trying to say is here we have a pressure distribution diagram. In this diagram, we are supposed to deduce what is the condition, soil condition or the loading condition available. So the effective lateral earth pressure distribution for the retaining wall support and backfill is given below. Which among the following option is best possible? So here one thing that we can do is two of the options are shown as layered and two are homogeneous. It is quite clear that it is not homogeneous because we have a shift at this point. So since we have a shift at this point, I can say that these two this is soils are different, and this is greater than 5.1, because stronger the soil, our Ka value Ka2 will be less than Ka1, and our lateral pressure will be lesser. That's why there is a shift, sudden shift. So I can say that it is either A or D. Second option is either it has to be C5 soil or cohesionless soil. If it was cohesionless soil, if we need a flat like a pressure, already if we need a lateral earth pressure at the top at z is equal to 0, then either we need a cohesion, passive cohesion, or we need a surcharge. But it is already told that there is no surcharge and it is cohesionless soil, so it cannot be this. So it has to be D. So let us just check. C backfill with under passive earth pressure. So C5 soil, when we have passive, we have 2C root Kp at the top. So this is that value, earth pressure without surcharge. So our correct answer is D. I would encourage you to go through this thing. So this thing will solidify our concept better. So I would suggest you to go through different problems without checking the question. Just see the earth pressure, lateral pressure distribution, and try to figure out what kind of uh, loading or soil condition that we have. So if we are trying to get it properly, that means that we are getting it with the bigger picture, right? So that is also a good exercise to strengthen our basics. So with that, I'll wind up today's session. So please share any doubts if you have. You can use the comment box also. You can also use our discussion forum in our portal. I hope it. In the last session, I had demonstrated how to reach that. You can post a question there also. Yeah. So um, if uh, if everything is fine, we can wind up. Thanks for joining again. We will meet you soon. The next session is by Sipshankar Nanti on the coming Saturday. We'll meet you on. I will meet you on 10th. Thanks for joining again. Have a nice day.